Apple II forever, making life better and better. Apple II forever and ever, bringing the rainbow to you.
Yeah, so at risk of burying the lead, like here it is, it works. You know, it's not just fictional. So got this running on a GS here that Jeremy ran, very graciously allowed me to borrow since my hard drive crashed yesterday. So after the talk, you know, feel free to come up and play with it on real hardware if you feel so inclined. All right. So there we go. Perfect. All right. So this is kind of a 3-year journey of playing around and experimenting. So back in 2022, actually 2021, I kind of got back into the Apple II community, pulled up some old projects I've been working on, and kind of got over some technical hurdles on this generic tile engine piece of software that I had started working on way back in like 1998, 1999. And did a presentation on that at the virtual KansasFest that year. So then over the following year, I was kind of working toward a 1.0 release, squashing some bugs, and it was getting into the spring, and I thought, well, I need to like make a game with this. I need to show something more than just some tech demos. And since I'm terrible at actually implementing games, all right, so then the next year I was kind of working to get a 1.0 release and thought I should try to get a game together. And since I can't actually implement games, I was looking around. I was aware that there was this Super Mario disassembly that was sitting on GitHub for a number of years, and thought, well, you know, this game engine, I designed it to try to be in line with how hardware worked in the Nintendo Genesis era. Let's give it a shot. Let's see if I can get something running using that source code, but my graphics engine. And it kind of fell into place. It was just a couple of weeks, and the graphics were working, and things came together. And I kind of did a last-minute presentation of that online at KFest last year. And so that kind of inspired where I took the project over the last year, which was to now separate out anything that was not related to supporting the NES hardware and try to make a really clean and direct hardware abstraction layer to be able to port NES code back onto the Apple IIgs and have a runtime that supported a lot of those hardware features. Just to be clear, you know, this is not an emulator. This is meant to start from some disassembly or some NES source code and then give you a pretty clean way of moving that source code and retargeting the Apple IIgs as a runtime environment for it. It doesn't run NES code unaltered in any sense. So between last year and this year, these were kind of some of the things that got changed in the source code, so making it align with the Nintendo screen size, a lot of optimizations, a lot of PPU support, things like that. So taking a step back, this is kind of what the overall goal was, is to make a software version of this. So here's, you know, kind of a schematic of the Nintendo hardware. There's kind of the 3 major components. You've got the CPU, you've got the picture processing unit, and then you've got the audio processing unit, which is integrated into the CPU on the NES, and then a small amount of RAM, both dedicated video RAM for the PPU as well as some working RAM that the CPU can directly access. And so here just kind of broken into the block diagram. Now these lockout chips, they're just for hardware. They made sure that, you know, Nintendo seal of approval, you only get official games. We don't have to worry about emulating those. And what's interesting about this here is that you can see the green, the picture processing unit, all the graphics side of the Nintendo. It only talks to the CPU over this one very, very narrow bus. Everything on the NES, similar to on the Apple, is memory mapped I/O. So there's actually a very small number of memory mapped I/O registers for talking to the PPU and also for the APU, only about 16 or so on each. So you're not talking about a particularly large surface area to implement. So you know, overall, when sort of planning this out, the goals were, well, we needed to run the code natively. There was no way to run any sort of emulation or simulation. That just wouldn't work. The GS is faster than the NES. NES runs at 1.79 megahertz. GS is a little faster, but we're doing all the graphics and software. We need all the cycles we can spare to do that. The Ensonic, of course, is much more capable than what the APU is on the Nintendo, so the hope was, okay, find some way to translate what the sound should be and just have the Ensonic emulate that. and basically get our audio for very low or zero cost. And then the assumptions, the hopes, fingers crossed, is, I kind of understood that NES games did most of their work in vertical blank. So it was sort of the hope of maybe they did all their work in vertical blank, and I would have most of each VBL cycle that I could dedicate to doing the graphics rendering and get something that was actually usable. And then opportunities to cheat. Are there things that the NES is doing that we don't have to do? NES supports 64 sprites. There's not always 64 sprites on screen. So were there going to be fast ways to ignore most of what was happening there so we could try to optimize the software rendering? So this is kind of the major components that actually got implemented. So you can see those same block diagrams from the previous slide, broken down our cartridge, our CPU, and then the PPU. And then these are the different memory mapped I/O locations that are used to command them. So you can see there's not very many of them, like I said. The main things to keep in mind here is basically how all this stuff is driven. Everything is pretty much interrupt driven on console games. They're running at the locked 50 or 60 hertz. There's other systems that are being clocked at a constant rate. So for the Nintendo, there's the VBL interrupts that drive all of the primary screen updates. So those are happening every 60th of a second. And then on the audio side, it's getting clocked at 240 hertz. That's basically the internal state machine of the audio processing engine. You set up your audio parameters, things like fades and sweeps and things like that. And then they'll be updated based on every 4 milliseconds or so when these counters fire. So at a minimum, needed to have interrupt sources to be able to drive these pieces of code, and then also be able to figure out how to intercept and then emulate the effects of the writes for all of the different memory mapped I/O registers. So as a starting point, we had those pieces of the Nintendo hardware. Well, where are we going to fit them into the Apple IIgs? Where are these different components going to live in Apple IIgs memory space? Well, first of all, the work RAM, the 8K of work RAM that the NES had, that gets split up. So we have some work RAM and some bank in memory where we're going to load our Nintendo code. And then the 0 page and the direct page, they get shoved into bank 0. We don't have to actually use 0 page and page 1 for the stack. We can use the stack pointer and the direct page register to put them somewhere else, but they're not going to live at the same addresses that they would live in in native code. And then the actual program ROM that lives on the top half of some allocated bank. And then we've got another bank where we kind of hold all the PPU data and RAM as well. There's not much there. So there's only 8K of character ROM. Those are all the sprites, the tiles, all the graphic data that a ROM has. And then there's the name tables, which they take up 2K of RAM, but they actually they take up 4K RAM, but there's only 2K of RAM backing them. So they're mirrored in different directions, which is actually configurable in the hardware. The one thing you'll notice here is I have kind of these grayed out areas in between the areas that are allocated to the NES space. So in the bank N from address 800 to 8000, that's not mapped to anything on the NES. So that's a place where we can take advantage of that and put in shim code, support code, do whatever we want with it. It's free RAM space that doesn't exist. Nothing's going to call it. Nothing's going to store to it. So that's the point that we can get in and start to manipulate and provide ways of shimming the code. And then similarly in the PPU space, have this big block that says shadow data. That holds a whole bunch of extra support data that tracks the state of the PPU in order to pretty much take care of rendering things quickly. It pretty much caches writes, caches other things, because no matter what, we're never going to have the Apple II render 60 frames per second. So at best, you might have 5 or 6 NES frames get executed before you finally catch up on the 2GS side. So those have to get queued up and then processed later. And all that shadow data is there to kind of support that deferred execution of all of the graphics updates. Okay, so now how do we actually implement the audio and the graphics side against all of this stuff that we've scattered all over the 2GS RAM? So the audio is actually pretty easy because the audio is write only from the code side. The NES can't read anything from the sound registers. It can only write new data. So it's a one-way data stream. So what happens here is, the code is executing, we intercept it, basically replacing loads and stores with jump to subroutines, and then update our internal APU state that we're tracking. That happens whenever anything is executed on the NES side, and then that 240 hertz interrupt that we talked about before, that's generated by the Ensoniq. We take one of the oscillator pairs, configure it to generate interrupts at that rate, and then every time that interrupt fires, the handler looks at what's been updated for the APU state and then takes care of updating whatever Ensoniq registers we need to replicate the sound. The hardest thing with all that is, really was the mapping, because how the NES sound is characterized is not how the Ensoniq characterizes. So the work it does is basically mapping it's basically counters and timing parameters on the NS side, and then those have to get mapped to the frequency registers on the Ensoniq side. So there's a little bit of calculation happening there, but fortunately it ends up being mostly just shifts and adds, and it happens fairly quickly. The PPU side is it's a lot more complicated than that. So there's a lot of things that go round and round here, but I'll just kind of give you the high level gist. So we key off of the VGC VBL interrupt. So every 60th of a second, we get an interrupt. We call the NES ROM code so that it runs at its normal 60 hertz pace. And then when it's finished, we get control back. And everything in the runtime is running this apply PPU updates. That's why it kind of has the infinity symbol there. That's what we're trying to do all the time as fast as possible. Is just look what's been updated on the screen, render the screen. Look what's updated on the screen, render the screen. Everything else is happening by interrupts in the background. And then also, I found this out when I was porting the second game. So kind of as a side, so the first game I ported was the Super Mario Brothers ROM. That's what I did last year. That's a very nice bit of code. So what it does setup, and then the ROM just drops into an infinite loop, and everything it does in terms of gameplay logic or updating registers happens in its interrupt handler. So very nice and clean. We get an interrupt on the GS side, we call the ROM, we get control back, we render the screen, rinse and repeat. The balloon fight game does things differently. It does all of its logic in sort of the main thread, the code that goes from the reset vector, follows through, it never enters into an infinite loop. It keeps doing the game logic, but it busy waits on the VBL flag in a bunch of places in the code. Okay, put the title screen up. Now busy wait on the VBL flag 10 times to delay for a 1/6 of a second. Repeat in a bunch of different places. So that was problematic because we weren't getting control back from the ROM. It would just sit there and basically spin until something happened and there was no opportunity to update the graphics. So that's what this yield arrow is in there. The runtime has a yield function that can be put into the ROM code to say, well, if you're busy waiting on a VBL, I'll give you control back when the next interrupt comes in, but you need to yield control back to me so I can do some work while you're just sitting here busy waiting on a flag. And so that's kind of one of the big ways the runtime cheats with these games, is to get as much CPU time as they can back by essentially making the ROMs a kind of cooperative multitasking system between the runtime and the actual game code itself. So at a really high level, it really comes down to just kind of like 6 functions to wrap a game. We set up the game configuration, we start up the virtual NES, set up its palettes. Palettes are special because the color mapping is kind of complicated between the Nintendo and the 2GS. The Nintendo can have 25 colors on screen. Obviously, we can only have 16 easily on the GS. So the runtime provides a lot of support for mapping down those functions, but it requires some additional setup. Then we go into the cold boot, call the reset vector, and then we drop into this main event loop where pretty much everything is firing off of this VBL I talked about before. And then we keep running the game until the user decides that it's time to quit. The game config, I just want to call out kind of quickly. There's a lot of things that it can tweak. Pretty much all these are just ways of trying to do less work, but the only way you can know what to do less work in is by understanding the game you're trying to port. So these are all ways of injecting game-specific behavior into the build. So one in particular, I'll just kind of explain, is this direct OAM read. So normally, when a game is getting ready to draw a new frame, it's updated, sprites on the screen, bullet positions, character positions, whatever. They build that up into an array of memory, usually 256 bytes long, and then they execute. There's a register called PPU DMA write, and when you write to that register, what it does is it does a DMA from the Nintendo memory into the OAM memory in the PPU. So it's fairly quick because it's DMA on hardware. But if we had to do that simulation in software, we're copying 256 bytes, which isn't terrible, but even if you do that fast, you're talking 7-8 cycles per copy, times 128 if you're doing 16-bit copies, something on the order of about 1,000 cycles to copy that data. And because this is something that's instantiated from that VBL interrupt, you're doing that 60 times every second. So it adds up to a fair number of cycles in terms of a total 2.5 million cycles or so to work with. So if we can avoid that, we can. And in a lot of cases, we can, because the data is already set up in the Nintendo's RAM. So why not just read it from there? Why do the copy at all? In some cases, it doesn't work, but if it does work for a game, we can set this flag, and we can see here on the PPU DMA write, if it's set, we just return immediately. Don't even do any work at all, 0. And then when it's actually time for, when we finally get some cycles on the 2GS side to render some graphics, then we go in and rather than reading it from this PPU OAM copy region, we just read it directly from RAM in the NES ROM space. So we avoid that extra load and store, and it adds up over time. Because when we're doing the copy in here, that's only happening once every time we render a 2GS frame, rather than doing the copy here, which happens once every VBL. All right, let's look at some pretty pictures. That was like a lot of dry stuff, but that's how it's all put together. So the reason that we have to do all that cheating, and kind of that's where most of the effort was put in the runtime, is pretty much summed up here. That game logic gets locked at 60 frames per second. Generally, you're looking at less than half of the CPU time left to do all the graphics rendering. So, and that's not just like going in and doing a screen blit. It has to go in and then parse all of the NES sprite data, figure out where things are on the screen. All that housekeeping work that goes along with just the raw movement of graphics data. But here's how it kind of lays out in practice. So for Super Mario Brothers, these are kind of some of the core parameters that got set up in order to structure the game to render correctly. So kind of top to bottom, first thing is we make a custom screen rendering function to take care of that fixed status bar at the top. On a real Nintendo, they do what's called this sprite zero-hit testing. The first sprite is special, that there's actually a hardware flag that will be set when the scan line actually intersects that particular sprite. And that's used in order to make these split screens. So in the code, the original code, there was this tight loop that just spun waiting for this sprite zero flag to be hit, and then it would change the hardware registers to shift the scroll, move the screen over, and that's how you got the fixed top and then the scrollable bottom. Well, like I said, trying to kill every busy loop we possibly can in the code, so I don't even process sprite zero. Instead, we just make a custom rendering function, and on the 2GS side say, well, we know the screen's supposed to look like this, So I know to draw these few lines a line left, and I'll draw these lines where they're supposed to be, and I won't try to emulate what the Nintendo is doing. I'll just sidestep it and then replicate it visually. And since I'm skipping sprite 0, then I'm only going to look at 63 of the 64 sprites because I know I'm never considering that. Not a big win, but every little bit helps. And then also, as you can see here, a lot of times all the sprites on the screen aren't actually visible. A lot of games do use these fully transparent sprites in order to keep things consistent. So the Mario character here, it's rendered by a 2x4 grid, so it can be up to 32 characters tall, because that way they don't have to change anything internally when you get the power up and you grow it to large size. You're still using the same number of tiles to represent that character. Same thing with the enemies. The Goombas are only 16 by 16. If you get a Koopa, well, it's bigger, but everything is 2x3 tiles. So if we're rendering things that are blank, just skip them. It's like we know we're looking at all this from the per game perspective. So we know that that's a blank tile, so we're not going to draw it. Other games might have different blank tiles. We'll put in different tests to look for those special tiles. And then also things that are off screen, we'll skip. And the sprites do get put off screen pretty normally, but we only have 200 scan lines on the 2GS instead of 240 on the Nintendo. So we're always going to have a shorter screen so we can be more aggressive and clip tiles that would normally be on screen because we don't see them here. Balloon Fight, very, very similar, where, again, custom render to keep the status bar in place. This one is primarily a single static screen. It doesn't scroll very much, so there's a flag you can set to enable dirty rendering. So only scan lines that had deltas between the previous 2 frames will get updated. That gives a pretty good boost for games like this. And then also the rest of the things are pretty similar. We're hiding transparent tiles, off-screen tiles. This game was a little bit tricky because I actually had to end up using 3 different palettes to make the color scheme work. So there's some overrides for when the PPU updates palettes where we have to go in and say, okay, this color actually needs to be replicated into palettes 1, 2, and 3 on the 2GS side in order to make the colors remain consistent. So there's always going to be little fix-ups like that. Okay. So at this point, I'm just going to show kind of how these look live, and then in 5 minutes, we're going to go through how you port a game from source and make a live version of it run. All right, so this is the ROM here running in the emulator. So all the things that we talked about, the fixed screen, how all this stuff works out. What is the jump button? It's all in place. One thing you can see is that the movement is a little bit staggered. So just like in most 2GS games, it's rendering at 1 byte at a time. So I only have an effective horizontal resolution of 160. So sometimes mapping between where the scroll is on the Nintendo side versus the 2GS side, it doesn't quite line up, and things get a little bit, you get a little bit of stutter in it, but it's usually pretty good. And most importantly, the placement of things relative to the background is fixed. There was a bug that I fought for quite a while, like on this Fire Flower, where as you would move along, the power-up would kind of shift like 1 pixel back and forth because it would be just slightly misaligned with the sprite coordinates versus the background coordinates. But we got that sorted out, but there are a lot of like little things like that that ended up having to get solved. And then on the balloon fight game, so this is one that uses dirty rendering, so you get kind of better performance on that. And plus, I don't know if people who play Balloon Fight might notice, but one trick I use here is that I actually disable the background star twinkle field in order to get less updates per frame. But if that's something that you like, they all have built-in configs, so we can go back and re-enable things like that if you're willing to take the performance hit. So in addition to the sort of static things that we do to set up the animations, you can also have per game hacks and enhancements that you can toggle on and off within the framework. All right, and I'll try to finish up this fairly quickly. So kind of as an example, there's this homebrew game out there, Lights Out, that was programmed by, I've got the name on the slides, I'm forgetting at the moment. But it's a very, very simple game. It's only 2 kilobytes of code. Very, very small palette, no animation, single static screen. A lot of things that are really easy. So the first step of getting Nintendo a bunch of source code to run under this runtime is get the code. So this is for the code from the Bumbershoot, Michael Martin, the Bumbershoot GitHub, and you can see it's whatever assembler he used. It's not it's not Merlin, it's not Orca. So the first step is getting the code moved over and just getting it to compile, getting the syntax updated, things like that. So we do that. So we have something that builds. It's wrapped with those functions I talked about. Do the startup, do the setup palettes, do the cold loop, drop into the event loop, wait until the user says quit, and then we do the shutdown. And if we run this, nothing happens, can't quit, because it's all the original code. The first thing it did was disable interrupts and go into a busy wait loop, waiting for a VBL to happen that never happens. So the next step in porting it over is to take code like this, which is hitting these registers directly. We comment the ones out that don't matter, and then we'll replace code like this with jumps to the HAL layer. So we'll be able to replace these functions as is, and then once that happens, do another build. Nothing on screen, but we can quit. So we actually have control over the runtime now. And so then the final step is going in and doing things like setting up the palettes, linking in updates to the palette register rights. This can be pretty straightforward for games like Lights Out, because if you look at Lights Out, what it's actually doing for like its palette, it only has 4 colors total. So super easy direct map to the 2GS. We don't have any palette issues. We can just take one palette, use it for everything, hook that into the runtime, and then end up with a result like this. And now it's running. They only use a single sprite for the pointer, and everything else just works as you would expect. Yeah, all right. For the people who are awake, it was cool. Yeah. All right, so where to go from here? So kind of the next steps. Right now, it only supports what are called NROM games, so games that don't use any of the NES mapper chips, which are basically allow bank switching and more memory for each game. So looking to add support for MMC1. That's going to open up a whole lot of new games. I only support vertical mirroring right now, so got to try at least one game with horizontal and a few other things. So you know, there's definitely improvements to work on over the next year, but hopefully going to continue to release more ports in fairly short order. And you know, the more support it gets, then the quicker the next set of games come. So thank you for all sitting through this talk with me. Appreciate it. Let's open it up for questions if anybody has any. Ken. Why balloon fight? Mostly because it was a single screen game, and I wanted to get something to get the dirty rendering working, and I found a disassembly of it that was fairly easy to work with. I had thought about doing Donkey Kong next. There is a disassembly that I found, but it's a disassembly of like the Wii U Virtual Console, so it has like different variants of the Donkey Kong in the same source code. So basically it was the first decompilation that was easy to work with that I found.
How about two-player games?
Yeah, it supports both of the joystick ports, and that will work because right now it does support SNES Max, so you can plug in a controller, and you can use either two SNES Max controllers for two-player, or you can do one SNES Max and the keyboard, and you can get them assigned to both of them. That config stuff that I showed you, that's kind of baked into every game. I don't have the second player input configuration exposed in that yet, but it's implemented in the core. Oh, yes.
I understand that the NES runs a modified variant of the 6502 and in the distant future, doing great stuff already. Is it possible that NES runs a modified version of the 65816? Is that something that's possible, or is it something else?
So that was a two-part question. One about whether I knew about that the NES was a modified 6502. Yes, and I was actually worried that there would be some subtle differences that just running the code as is on the GS would cause a problem. Haven't found an incompatibility yet. Not to say that that's not going to happen at some point. And then the second part was about whether this could be extended to do SNES games. I don't think so. The SNES just has so much more going for it, especially like with multi-layer support and things like that. Not to say that maybe you couldn't do something that would run it, but I don't think you could eke out the performance to even make it anything desirable. But I'd love to see someone try. All right. Well, thanks again, everyone.